Hello everybody and welcome to the module on hyperparameter optimization. I'm Lars Kotov, and in this video we will talk about configuration spaces, the types of hyperparameters that they are, their relations, how they work together, etc. So hyperparameters can have many different types depending on what they described. We have in the previous video already had a look at some of the examples. And often hyperparameters can take different values, but only some of them will make a difference in practice. And if this is a structural issue, then this is something that we want to encode in the space that we search through so that we can search more efficiently. Because hyperparameters can depend on one another, and specifying this well and specifying this in a way that the search can take advantage of it can make a huge difference for hyperparameter optimization in practice. So we want to specify the configuration space well, because otherwise we might have a search that spends a lot of time looking at things that do not actually make a difference in practice because the configuration space was misspecified. What different types of hyperparameters are you usually considering? So we can have categorical hyperparameters or strings. So these would usually be specified as strings when you write the code. This can be, for example, the type of kernel for a Gaussian process, a distance measure for your k-nearest neighbor classifier, the booster type for XGBoost, or many other different things for other types of learners. Then we also have integer or ordinal hyperparameters. This would be, for example, the number of trees in a random forest, the value of k for k nearest neighbors, so how many neighbors should we take into consideration when we decide what value to predict, or the degree of the polynomial in a polynomial regression. They can also take real values, for example, the learning rate for a neural network, regularization hyperparameters for support vector machines, or the minimum impurity decrease when we're splitting a leaf in a tree. So many different types, and depending on what they are and how they interact, we of course want to specify them appropriately. Which brings us to how we actually specify these in a way that we can search over them, which is as hyperparameter ranges. For the categorical type, this would usually just be a list of values. For example, Gini, entropy, log loss as the splitting criteria for trees. They can also be bounded ranges of values. For example, the fraction of observations to sample for a tree in a random forest. So these can be both real and integer, depending on what the hyperparameter is. And we can also have unbounded ranges. For example, the number of trees in a random forest, which is unbounded towards one side, because we can, at least in theory, make this as large as we want. Now, of course, you do want to determine these carefully in practice. For example, it doesn't really make any sense to train a random forest with 1 million trees in it, because if at all you're observing an increase in predictive accuracy, then it's going to be very marginal and it will take a really long time to train these. So you do want to be careful when you specify the ranges of hyperparameters in practice, so that you don't accidentally include something that is unlikely to give you any improvement, but will, for example, take a very long time or a very large amount of memory, or both, to train, because that might then cause issues with your search. We can also have dependencies between hyperparameters, where the value that is set for one hyperparameter affects what others can be set to. For example, if I increase the maximum depth of a tree in a random forest, for example, this will only have an effect if the minimum number of samples per leaf is set essentially high enough. So and here you can already see that this can be very subtle in practice, because it doesn't necessarily only depend on the learner that you're dealing with, because it also depends on the data set. So you do have to be careful about this in practice, and that might in particular mean that when you're specifying the configuration space to search over, you might want to have a close look at your data set and see whether it makes sense in this particular context, because you do want to optimize hyperparameters for a particular data set. And there you might want to include values or exclude values that for other data sets might make sense. Some hyperparameters may only be active if other hyperparameters are set to specific values. So the classic example here would be that the degree of the polynomial kernel in a support vector machine is obviously only meaningful if the kernel is indeed said to be a polynomial kernel and not another type of kernel, and there are other examples of this as well. So specifying all of these dependencies can be very complex, in particular because this is not necessarily obvious. This is something that you need at least a little bit of expertise to. Hopefully most of these dependencies would be documented for the respective learners, but in some case they might not be, or in some case they might not be explicitly documented, but as I said previously, they might depend on properties of the data set, and then you have to realize that, oh, hang on, actually here is something that will have an effect there, and I do need to take that into account when I specify my configuration space. So yeah, we call the combination of all possible values for hyperparameters that we want to optimize over a configuration space. So this is essentially the space in which we search for a hyperparameter configuration that will give us the best performance on the particular data set that we're dealing with. Predefined spaces are available, in particular from AutoML tools, so you can download your AutoML tool of choice, and that will already come with a configuration space. In practice, specifying this, as I said, is not entirely straightforward. So if you do want to write your own AutoML tool, or you even just want to specify your own configuration space with an existing AutoML tool, you do have to be very careful with this, and this does take quite a lot of effort. An additional complication in practice is that very often you want to use transformations that will not change the space, but will make it so that we can search it more efficiently. For example, changing the number of trees in a random forest on a log scale. Because if you're going from, say, 100 to 101, that is unlikely to have a large difference, and therefore you're probably wasting an evaluation if you try both of these values. So you want to make a larger change there, whereas on the other hand, if you're changing from 5 to 6, that might already make a large difference because the number that you're starting from is smaller. So there are lots of things that are relevant in practice here that you do have to be a little bit careful with, but in the end a lot of these will be taken care of by existing AutoML tools as well, and if you use one of those, then you don't have to worry about it too much because it will come with a configuration space that is set up in a sensible manner. The extension of this would be to look at learners themselves as categorical hyperparameters, because you might want to not only optimize the hyperparameters for a particular learner, but you also want to know which one is actually the best learner. That can also be non-obvious for a given data set, and if we start optimizing, well, why not optimize this as well? Now the good news is that there's no fundamental difference between optimizing the hyperparameters of a learner and what learner to use. What you end up with is a configuration space that is, of course, larger and more complex because you now need to encode these hierarchical dependencies. If I have chosen this particular learner, then these hyperparameters here become active, whereas if I use the other learner, then this different set of hyperparameters will be active. But you can specify this in the same way that you would specify any other hierarchical dependencies, and then use your favorite AutoML tools to do the optimization. This is often called cache in the literature, and there's a reference on the slide here if you want to know a little bit more. It is more challenging to optimize in practice, but we don't need to leave that paradigm. We can apply the same fundamental tools and the same fundamental approaches here. So in summary, hyperparameters can occur in many different forms. Hierarchical dependencies allow to encode the hyperparameter spaces of complex systems, in particular systems where the choice of the learner to use is one of the hyperparameters, and determining what hyperparameters and values should be considered for optimization is challenging in practice. How large should the ranges be? Should we include this hyperparameter or should we not include it? It has never made a difference before. Is it going to make a difference here? These are difficult questions that you have to answer in order to do good hyperparameter optimization in practice.